Here is a quick tour of the garden. You'll see I have a lot of spinach growing from last year. You'll see I have some collards still growing. Nothing really left from last year. Here I've planted my lettuce and some spinach and some rhubarb and lots more lettuce and spinach starting to come up. Good morning. I'd like to welcome you all to day 4 aboard the Axiom. Today we're going to finish up the magic of moving charges. We want to start with a very important idea, and that is if a charge is at rest, it will not feel a force from magnets. No matter how strong these magnets are, this charge will not be affected. However, if we move the charge, all of a sudden that charge feels a force from those very same magnets. We can see this with this red wire. I'm going to run electricity through this wire. The wire is inside a magnetic field, and if you watch that wire, it will pop out of that magnetic field because of this magnetic force. Again, you can see it here. I've got a wire in between the poles of a magnet. Nothing is happening. The charges are at rest. But now all of a sudden, once the charges start to move, they feel a magnetic force. So what's going on? Well, we saw this one last time with our rail gun. We ran electricity through this rail, and this rail all of a sudden started to move along the tracks. Okay, so why is it that this force only happens when this charge moves? This is the big question for today, so make sure you understand this idea. Why does this force only exist when the charge is moving? Well, it turns out that if you have a charge that's moving, that charge will be surrounded by a magnetic field. The charge is always surrounded by an electric field, but when it starts to move, a new field springs into existence, and that field is our magnetic field. Here is the formula to figure out the strength of that magnetic field. The B is the strength of the field created. It's measured in Tesla. The V is how fast the particle is moving. That's obviously in meters per second. The Q is the charge in coulombs. R is how far it is from the center of the charge to the spot where we're measuring the field. And this is a new universal constant for you. It's called the magnetic permittivity of free space. And you can look up its value on your reference sheets. Now, we know that this charge is surrounded by a magnetic field. So when this charge enters into an already existing magnetic field, these X's are not caused by this charge. They are already there. They are caused by external magnets. So when this charge enters into this field, the field from this charge interacts with the pre-existing field, and it creates a force. So once again, the force is created by two fields interacting. The field that it was already there, and the field from this moving charge. We can see that this is reality by putting a compass near a wire. The compass will point in its normal direction until we run electricity through the wire. When we run electricity through the wire, all of a sudden the compass will deflect, and that shows us that the moving charges in the wire are creating a magnetic field. It turns out that that magnetic field creates a circular loop around the wire. It would look something like this. So here's my wire. It's carrying current from right to left. Surrounding the wire will be a magnetic field. And you guys can see that that magnetic field creates circles around the wire. This is the spot where we're going to measure the magnetic field, and this is the formula that will allow us to do that. I is the current flowing through the wire. R is the distance from the center of the wire to the point where we're measuring the field. And again, we have our magnetic constant, And we have on the bottom 2 pi times the radius. You'll notice 2 pi r is the circumference of a circle because these magnetic fields are forming circles that are looping around the wire. Now, are they circling around clockwise or are they circling around counterclockwise? And how do we know? This brings us to the second hand rule. This one is figuring out the direction of the magnetic field around moving charges. And what you do is you point in the direction of the current with your left hand, with your thumb, and then you wrap your fingers around the wire. Your fingers will wrap around in a circular pattern, showing the direction that the field wraps around the wire. So in this case, you could see that above the wire, our fingers are coming towards us. You could represent that with a series of dots above the wire. And below the wire, our fingers are going to be pointing away from us, negative Z direction. And we could draw that with a series of X's. So that's how you figure out how the field wraps, either clockwise or counterclockwise, around the wire. So here's a problem you could try. I have 3 amps traveling through a wire. I want to know the strength of the magnetic field 8 centimeters away. And I want to know, should I put X's or dots below the wire? Should I put X's or dots above the wire? So when you do this problem for me, don't just do the math. Don't just find the strength of the B field, but also put X's either above or below, and dots either above and below, showing the direction that the field is wrapping around this wire. Okay, now we have that same wire carrying a current through a magnetic field that already exists. I hope you can now see why there is a force magnetism on this wire. This is the current in the wire. It creates its own magnetic field. It interacts with the pre-existing magnetic field. That's the magnetic field that you see here with these X's. They are not caused by this wire. They were already there. And then L, that represents how much wire is actually in the field. Okay? So this magnetic force is caused by the field of the wire interacting with a second pre-existing field. And this is the one I'd like you to actually work through. This will be the second one you're going to figure out. I tell you the strength of the field, the length of the wire in the field, the voltage that's pushing current through this wire, the resistance of the wire, and I want you to figure out the strength of the magnetic field from the wire. I'd like you to figure out the force on the wire, and I'd like you to figure out the direction of the force. And I misspoke. You don't have to figure out the field from the wire, just the force on the wire and the direction of that force. We can see a use of this magnetic force. We talked about this a little bit last year. We run electricity through the wires. We put the wires in a magnetic field, and those wires will feel a force. And we could use that to actually spin a motor. So all motors are working off of this idea of moving charges creating a magnetic field that interacts with a pre-existing field to create a force. So anyway, these are our notes for today. I'm going to have some problems and activities for you online as part of your slideshow. I wish you guys the best. I know the weekend is coming up. It's going to be hard to have 2 days off where you really can't go anywhere, but try to do the right thing. Try to make sure you don't infect other people. Don't be a vector for this disease. Anyway, hope to see you all soon, and I will talk to you again on Monday.